In the last video, I talked about conservative vector fields. The reason we use the word conservative is because the concept of a conservative vector field is closely related to the physics concept of conservation of energy. So let me show you the relationship in this video. So we can begin with the work-energy theorem, which we derived previously. We have the integral over some curve of the force dot dr, changes the kinetic energy of a mass, so it's equal to the final kinetic energy of the mass minus the initial energy of the mass. So this is the work done by a force on the mass imports energy to the mass, where the kinetic energy of the mass is 1/2 m times the speed of the mass squared. Okay? Conservation of energy occurs when the force is a conservative vector field. So if F is a conservative vector field, then we can write F equal to the gradient of a potential. And to get the conservation of energy law, we usually introduce a negative sign here. Okay? So what does that give us if we then compute this integral using the gradient theorem? So the integral, the work integral of f dot dr over the curve is equal to the negative of the integral over the curve of del v dot dr. And then using the gradient theorem, that's the negative of the final value of v minus the initial value of v. And then using the work-energy theorem, that's equal to the final kinetic energy minus the initial kinetic energy. Okay? Can we put all the initial terms on one side and all the final terms on the other? We have a negative vi and a negative ti on the right. We put that on the left. We end up with the initial kinetic energy plus the initial potential energy. We're going to call v the potential energy, is equal to, put all the finals on the right, the final kinetic energy, and then we have a minus vf goes to the right, plus the final potential energy. So the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And that's the expression of conservation of energy. Okay? So the kinetic energy is quite simple, 1/2 mv squared. The potential energy depends on the force. So it depends on finding a v such that the force is equal to minus the gradient of v. And v is the potential energy. So to work a problem using conservation of energy, which I asked you to do as one of the reading problems after this lecture, you need to know what the potential energy of the force is. So the reading problem has to do with gravity. So what I should do in this video then is show you what to find the potential energy of a mass little m in the gravitational field of a mass big M. Okay? And then you can use that in your reading problem to compute the escape velocity for a mass from the surface of the Earth. Okay, so how do we set this up? So we have a mass big M. We'll put that at the origin of our coordinate system. So this will be our mass big M. And then we have a mass little m, we have a vector r from big M to little m, right? And then what is the force on little m due to big M? So the force is the gravitational force. It's a force of attraction, so it's pointing in the negative r direction. So we usually put a minus sign. There's a gravitational constant g. There's the product of the two masses, mm. And then it's an inverse square law. So we can write the inverse square law by writing this as the r vector divided by the length of the r vector cubed. Okay? That's Newton's law of universal gravitation. So that's the force on little m due to big M. We want to know what is the potential energy of little m due to big M. So we have to write this as the negative of the gradient of a potential energy. So to do that, we use the following. So this was one of your reading problems. The gradient of 1 over r turns out to be negative r vector over r cubed. So that was something that you should have done as a reading problem. So then this force we can write as, we have a negative r over r cubed, so we can write that as g m big M, little m big M, and then we have a gradient of 1 over r, right? We can go ahead and pull the gradient out. So this is the gradient, or it's going to be the negative gradient of whatever is left over. So we have a negative g m m over r. Okay? So we can write the force as the negative gradient of some scalar field. So then we get the potential then of the little mass m in the gravitational force of big M is then given by minus g, the product of the two masses, divided by r. Okay? That's the potential energy. Okay. You'll need to use this then in the reading problem. So let me summarize. We talked about a conservative vector field. The reason we use the term conservative is because it's closely related to the conservation of energy that physicists absolutely love. We start with the work-energy theorem. So the work done by a force on a mass is this line integral of f dot dr. And that causes a change in the kinetic energy of the mass, the t final minus t initial. So if f is a conservative vector field, then we write f equals minus del v, and we call v the potential energy of the mass in this force field. Because then if we do calculate the work, then we can write it in terms of the potential energy. We can integrate this work integral. And the end result is that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. We have conservation of energy. We can use the conservation of energy law if we know the potential energy of a given force. Here I look at the force due to a mass big M on a mass little m. The potential energy of little m in this force field is given by minus g little m times big M divided by r, a scalar field. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.